We can also graph linear inequalities from standard form. The process is the same. First, we graph the boundary line, either dashed or solid. Just now we graph the boundary line by plotting the x and the y-intercepts. For a standard form linear inequality, we can't trust the greater than or equal to symbol. Therefore, we need to determine shading the way that we checked it for our slope-intercept shading. We need to plug in the point 0, 0. Let's go ahead and graph this linear inequality. 2x minus 3y is less than 12. First, we're graphing the boundary line, either dashed or solid. We need to do that by finding the intercepts of that equation. So the equation 2x minus 3y equals 12 gives us the boundary line. The x-intercept of the boundary line is found by solving this two-step equation. Plugging in 0 for y, 2x equals 12 divided by 2, divided by 2. There is not a lot of space here. X equals 6. That means my x-intercept is 6, 0. Y-intercept. Again, I need to pretend this is an equation. I'm graphing the boundary line. Negative 3y equals 12. I'm trying to write really small. Divided by negative 3, divided by negative 3. The y-coordinate of the y-intercept is y equals negative 4. So my y-intercept is 0, negative 4. So far, this is exactly what I would be doing if I were graphing the line 2x minus 3y equals 12. However, now I'm graphing a linear inequality, which means a boundary line and a shaded region. I need to determine, is my boundary line dashed or solid? This part's the same as slope-intercept form. If there's an equals to sign, it will be solid. Without an equals to sign, points on the line are not solutions, so my boundary line needs to be dashed. Is it dashed? Is it solid? Dashed. Dashed because there's no equality component. Dashed is, I was gonna say it's easier to draw straight, but that turned out not to be true. So there's my boundary line. The very most frustrating question that I get all the time in this unit is, do I need to shade? Is this one where I shade? Every linear inequality will have a shaded region. The solution to the inequality is those infinite number of points in the shaded region. Okay, I cannot trust that I'm shading below. I'm going to plug in 0, 0 to determine shading. For your reference, I'm going to show 2 times 0 minus 3 times 0 is less than 12. But really, when I plug in 0, the left-hand side becomes 0. Is 0 less than 12? Is it less than 12? Yes. So I do shade the region with the origin. I would have predicted that I should be shading below, so this should be a lesson to you. Do not trust the inequality. Plug in 0, 0 for standard form. If we transform this inequality into a slope-intercept inequality, you'll see why we could not trust that less than symbol. So let's go ahead and transform this into slope-intercept form. Do you remember how we do that? First, we move the mx term to the right-hand side by subtracting 2x. Then we divide by negative 3, which would more commonly be done with a division bar. Negative 3y divided by negative 3 is y. I'm dividing by a negative. What happens to my inequality? I hope you remember. It flips. Negative 2 divided by negative 3 gives me a slope of 2/3 x, plus 12 divided by negative 3, so minus 4. So if you are a super transforming rock star, you could graph from the slope-intercept form, but you can see that there's a lot of computation and this is pretty error-prone. However, transforming into slope-intercept form is really great for checking, so I should be shading above. That's what my slope-intercept inequality tells me. My slope is 2/3 up 2/3, and my y-intercept is negative 4.